Hello everyone, I'm Shubham Mangekar and I'm a first year PhD student at Peace Lab at ASU, and I'm currently working on my project title is a triple active bridge C3L3 converter steady state model and closed loop control. This is the hardware which I'm working on. I'll go into further details in the slides. So after the introduction, I would like to talk more in detail about the converter through these slides. And once we have the details, then we can go back to the converter, the hardware, and then we can look at the testing results, and we can look at the testing and the testing results as well. So the topic is triple active. The project is triple active C3L3 resonant converter steady state analytical model and loss optimized closed loop operation. And so first, before going into the project, we would like to look at the state of the art of power conversion in electric vehicles, where we see that we have two types of batteries. We have the high voltage batteries for traction, and we have the low voltage batteries for low voltage loads such as ACs and other ACs, fans, etc. And we see that we in the current state we use two different DC-DC converters, where one is used to transfer power from a constant DC bus, which could be 400 or 800 volts, and transfer it to a high voltage battery, which could be variable depending on the state of charge of the battery. And we have another DC-DC converter which is which is used to transfer power from the high voltage battery to the low voltage battery, and it is a bidirectional power converter, where it is also able to transfer the power from low voltage to high voltage battery. Now, after having learned the state of the art, let's move on to what exactly we are proposing in this particular project. So what we are proposing is a triple active bridge C3L3 type of converter, which can be with the block diagram can be seen above. So as you can see that it is able to connect the HV battery and the LV battery both at the same time, and it's able to transfer the power from the constant DC bus to the high voltage and the low voltage battery at the same time. The advantages are straightforward. That is, instead of two different converters, and there are two different cooling systems, we're replacing that with one converter. So and one cooling system. So obviously, it will have a system level reduction in the volume. Um, also, like also we're gonna reduce the number of semiconductor devices. So that's also semiconductor devices as well as the passive components within the converter. So that's also going to lead to a higher efficiency, higher system level efficiency. The challenges being the analytical model becomes complicated, and the control becomes much more complex, as we'll see further in the equations. Now coming down to the circuit diagram, as we can see that we have three active full bridges, which generate VP, VS, and VT, and the port currents being IP, IS, and IT. And as you can see, the arrows from the arrows, you can see that PP is the power flowing from the primary side to the tertiary and the secondary sides. PS is the power flowing in the secondary side, and PT is the power flowing in the tertiary side. So PP is going to be the combination of PS and PT. And at the output, we have a load ROS. The battery is being represented as a resistive load ROS, and the voltage across it is VOS. And similarly, on the tertiary side, we have a resistive load ROT, and the voltage across it is VOT. So if we have to draw an equivalent model of this particular circuit, we can replace the full bridges by a quasi square wave generating voltage source, and the resonant tank remains the same, but the resonant tanks can be represented as the inductors can be represented as impedances at different frequencies of and the harmonics. One more thing to note here is that the leakage of the transformer is being used as the resonant inductor, and the value of the resonant capacitor is chosen in order to achieve a certain value of the resonant frequency. Um, Having said that, let's come down to the design specifications and design objectives. So the nominal voltage at the input is going to be 400. The secondary side, it's going to be in the range of 500 to 600. On the tertiary side, it would be 24 to 28. And the rated power would be 2 kilowatt for the primary and 1 kilowatt each for the secondary and tertiary. And the turns ratio is 16, 22, and 1 respectively for NP, NS, and NT. I've also given the values of the leakage and the magnetizing inductance obtained from the characterization of the transformer, and I've also provided the values of the resonant capacitors which I've chosen for each of the tanks in order to achieve that particular value of the resonant frequency. The research objective for this project are to develop the analytical model for this converter to obtain accurate port currents. Now, why do we want to obtain accurate port currents? Because the port currents determine the losses in the system. So once we obtain the port currents, we want to develop the semiconductor loss model to estimate the converter losses. Finally, we want to control the powers, the powers and the voltages at the two different ports for the two different ports based on the requirement. That is the requirement of the state of charge of the state of charge and the charging profile of the HV and the LV battery. And we want to achieve all of this, keeping in mind we want to maximize the efficiency of the converter as high as possible at all the scenarios. So that would be another constraint while developing the model as well. Before going on to the model, it is imperative for us to understand what are the controls or degrees of freedom we have as a design or the control engineer or a designer. So in this case, we're able to control the switching frequency of all of the three active bridges. We're able to control the phase shifts between the secondary side with respect to primary, that is called as phi s. There is a phase shift between the tertiary side with respect to primary, which is called as phi t, and there is a internal phase shift between the half bridges of each full bridge, which is called as delta p, delta s, and delta t, respectively for primary side, secondary side, and tertiary side, respectively. Having said that, now uh, once I've defined those, let's move on to the steady state analytical model derivation. So, as I said previously, we can replace the three active full bridges by a quasi square wave generating voltage sources, and the impedances, the RLC network by the equivalent impedances, and we calculate each of those values at the harmonic frequency, the harmonics of the switching frequency, which we provide at the input. So once we do that, we obtain these equations, which is dependent on, which is obtained from the harmonic analysis of the quasi-square waveform. Once these equations are obtained, we can figure out the impedance. We can calculate the impedance values of each of those RLC network, each of that RLC network, and we can determine and we can solve this network further. In order to calculate the currents, the port currents generated inside of that resonant tanks, we need to do something called as superposition theorem. In that case, what we do is we have to break down the we replace the active voltage sources by a short circuit, and then we calculate the node currents for each the node currents because of each voltage source. And then once we do that and then we repeat the step for another voltage source and for the next voltage source, and then after that we add all of those currents together, and that would lead us to the final current, which would be similar to what we would see in an actual circuit. So this could be done because the circuit is linear, and it follows the principles of superposition. So once we follow the principles of superposition, we are able to derive the equations of the currents, the IP, IS, and IT currents. This is a huge equation, and it depends on the values of and it's dependent on the values of the voltage, the input voltage, the magnitude of the input voltage which we provide, the phase of the input voltage which we provide, the phase of the secondary side voltage, the phase of the tertiary side voltage, the frequency what we obtain at, because it's dependent on the impedance, and the impedance is a function of frequency. Hence, it's also dependent on the frequency, and also the deltas, the delta, the phase shift between each of the full bridges. So it depends majorly. It depends on six different variables which are previously mentioned. Those are our six degrees of freedom, which determine the currents flowing in the ports. Having said that, we do the power calculation. So as we said that PP is a combination of PS plus PT, and each of these powers can be calculated as per the formulas given above, which is we can calculate the active power of each of the port based on based on the multiplication of the currents and the voltages at that particular port, and the cosine of the difference of the angles of the voltage and the currents. So that gives us an active power, and based on that active power we can determine, that helps us determining what that helps us uh, that helps us figure out how much power we want to transmit at the load. um, once we are able to obtain all of these equations, we can solve them analytically to obtain a particular value of the frequency and phase and deltas. And by solving them analytically, we get those particular values based on a particular for a given for a given output voltage and output current, for a given output voltage and output power. We get a distinct value of frequency and phases and deltas, which we can use to run our converter with. So yeah, so having said that, this defines our control structure, wherein we use a controller. So in our case we're using the TI DSP for controlling our converter, basically providing the gate signals to our controller. And how it does is that, the way it operates is that it first initially we provided certain value of the power and the voltage we need at the output, and based on that, it solves the equations provided previously analytically to figure out the values of the frequencies and the frequency phase, and a combination of the values of frequency phase and the deltas. So for a given value of the given value of the output power and output voltage, it might have several different combinations of frequency and phase and deltas. And after that, once it obtains all of those values, it runs through the semiconductor loss model routine, and that loss model routine will generate the losses, the semiconductor losses at each of those different phase frequency delta combinations. And once that is obtained, then we try to minimize the semiconductor losses. We select the frequency, phase, and delta which has the minimum losses possible for the in order to achieve that same power and voltage. And from that we choose, based on the lowest losses, we choose the frequency and phase and the delta which is required. So that is how the frequency, phase, and delta calculation block works. So that brings me to the end of the conclusion of this slides. And now for the further clarification of the hardware, and now we'll look into the further clarification of the hardware. Thank you.
Welcome everyone. So I'll go over the hardware description of the project right now. As you can see, the hardware is being realized using a base PCB, and on top of that we have straight aligned active full bridges. The one on the left is the active is the primary side full bridge, which has the GaN system 650 volt rated device. So the input is provided at these two terminals, which is nominal 400 volts. The full bridge converts that input into a quasi square waveform, as is the case for the secondary as well as the tertiary side, and then provides that quasi square waveform to one of the windings of the 3-winding transformer. Coming down to the secondary side, so I'm going to align a little bit so that you can have a good visibility. So as we can see, we are using the GaN transform cascode devices 900 volt rated for this particular side, and the output voltage nominal 600 volts has been obtained at this particular two terminals, and then that is connected to a load such as an HV battery. Coming down to the tertiary side, so I'm gonna align it again, and you can see here that the tertiary side is being realized using this particular PCB. On this we are using the EPC GaN 2020 devices, which is 60 volt rated. So this is a low voltage high current side. The nominal voltage at this particular two terminals is the output is obtained at these two terminals, and the nominal voltage is 28 volts, and that is connected to the load could be something like an LV battery, low voltage battery. We are using 4 devices per switch positions on this particular bridge. The reason being, we want to reduce the RDS on. Paralleling the devices reduces the RDS on, and since this is being the high current side, we want to increase the efficiency by reducing the RDS on. Finally, coming down to the controller, so we are using the daughter card, this particular daughter board, which houses the TMS320F28379D microcontroller, which is being used to send the gating pulses to each of the active bridges. and we also have the auxiliary circuit. So at the input we provide 15 volts, which then converts back, which is then converted to 5 volts using this particular DC-DC converter, and that 5 volts is then being used to provide power to the gate driving circuitry on the 3 active bridges, as well as power to the microcontroller. And final part of this particular hardware description is the 3-winding transformer. So this particular 3-winding transformer was wound by me. The turns ratio on the primary side is 16, the turns ratio on the secondary side is 22, and the turns ratio on the tertiary side is 1. So that concludes the hardware description. Now we'll move ahead to the hardware testing of this particular converter, and we'll share the results. Okay, welcome back, guys. So here I'm talking about so this is the setup for the testing of this particular converter. So as you can see, I hooked up the input. So the input is nominal 400 volts, which is being provided. So I'm gonna take it down here. So which is being provided by this particular Magna power supply, which is 1000 volt rated. So this provides 400 volt at the input. At the output, we are using the electronic load, which is connected at this two terminals of the converter. And the third power supply is being used to provide the auxiliary 15 volts to the power supply, and the second part of the power supply is used to turn on the fan. So we are using, as you can see, we are using 2 fans to blow air on the semiconductor devices in order to avoid a case for thermal runaway. Furthermore, as you can see, I hooked up some differential probes. So one differential probe is probing the switch node voltages of the primary side active full bridge, and the other switch node is probing the output the switch nodes of the secondary side full bridge. And so that is the two differential probes. I'm using 2 current probes, one for probing the port current on the primary side, another for probing the secondary current, for probing the secondary side current. I'm also using these 2 cables to flash the microcontroller from my laptop, and I'm also using the RIS panel cable. So I'm using a software called as RIS panel to control my Magna power supply, which is this one, remotely from my laptop itself. So having made this setup, now let's see how it works. Hello. So I've turned off the fan so that we can discuss about the results. So as you can see, the waveform which I obtained. So right now, what I'm measuring the switch node voltages of the primary bridge and the secondary bridge, and I'm transferring power from the primary to the secondary. So, and also I'm measuring the current going out of the primary side full bridge and current coming into the secondary side full bridge with that orientation. So as you can see, it is important to understand the orientation of the currents. If you can analyze this particular waveform. So as you can see, when the positive, so yellow is the VP, blue is VS, pink is IP, and green is IS. So when the transition happens from minus V in to plus V in on VP, we know that switches S1 and S4 are turned on. In order for them to turn on, and at that time we can see that during the transition the current is negative. So that negative current ensures that the devices that the output capacitance of devices S1 and S4 is discharged because of that negative current, and that ensures a ZVS turn on. The advantage of ZVS turn on is obviously using a gallium nitride device, the turn on losses is minimized almost. It almost becomes negligible. So that is imperative in modern power converter systems to achieve ZVS or an SR condition. So in this case, we are achieving a ZVS condition. Similarly, on the other transition, when it goes from plus V into minus V in on VP, we see that the current is positive. So this positive current, because of its orientation, is able to discharge the output capacitors of the switches S2 and S3, and that also ensures the ZVS on those 2 devices. So during one switching cycle, we can see that 4 devices are undergoing transitions, but whenever they are undergoing ZVS, whenever they are going turn-ons, we can see that they are achieving ZVS because of the magnitude of the current and the orientation or the sign of the current at that particular value. Similar analysis can also be extended to the secondary side, where we see the negative VOS to plus VOS transition, and at that point the current is slightly positive, and that positive current is ensuring ZVS in devices S5 and S8. And similarly, during the negative transition, when it goes from plus VOS to minus VOS, you see that the current is slightly negative. So that also ensures the ZVS turn on for the devices on the second ZVS turn on for the devices on the secondary side. So I've given a demonstration of power transfer from the primary to the secondary.